If you were to board a ship traveling at the speed of light right now and flew in a straight line forever, I have bad news. You would never reach the edge. Space is stretching faster than you can run. But today, we are going to break the laws of physics. We will leave the Milky Way, cross voids so vast that light takes millions of years to traverse them, and navigate the cosmic web, those giant filaments that connect the universe as if they were neurons. Our destination is the final wall, the cosmic microwave background, the exact place where visible reality ends and absolute mystery begins. What does it really mean to talk about the observable universe? Is there a clear boundary that tells us how far our cosmos extends? The observable universe is, in simple terms, the region of the universe from which light has had enough time to reach us since the beginning of time. That is, since the Big Bang. Everything we can see, detect, or measure belongs to this gigantic sphere, which is not a real wall, but a limit imposed by the laws of physics and time. But how big is this observable universe? Although it may seem hard to imagine, it has a radius of about 46 billion light-years in all directions, even though the universe itself is around 13.8 billion years old. Why is this possible? Because space itself has expanded while the light traveled towards us, meaning that the objects we see very far away today are much farther away than they were when they emitted the light that now reaches us. It's like being able to see someone throwing a ball from the top of a mountain. But while the ball travels towards you, the mountain is moving away quickly. And how do we know where our cosmic vision ends? The limit is determined by the speed of light and the age of the universe. Light that comes from points too far away simply hasn't had enough time to reach us. Thus, the observable universe is like a bubble, centered on us. But each observer at any point in the universe would have their own observable bubble, with the same radius, but centered on their position. Does this mean that outside our observable universe there is nothing? Not at all. What lies beyond our reach may be infinitely vast, perhaps even much larger than what we can see. However, any region beyond this limit remains, for now, completely invisible and inaccessible to us, not because it is hidden behind a barrier, but because light, and any information, has not managed to reach here from those remote places in the cosmos. The observable universe, then, is not the total universe, but only the part that nature allows us to contemplate.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
The speed of light is much more than just an impressive number. It is the true speed limit of the universe. But have you ever wondered why this limit exists? Light travels at approximately 300,000 kilometers per second in a vacuum, a figure that defies imagination. However, no matter how fast it is, light takes time to cover cosmic distances. When we look at the sky, we are actually seeing the past. The light from the nearest star, Proxima Centauri, takes over 4 years to reach us. Thus, every corner of the visible universe is determined by how far light has been able to travel from the origin of the cosmos to today. Why can't we see beyond a certain point? The answer lies in the speed of light itself. Imagine the universe as a vast ocean and light as waves propagating from each event. We can only see as far as those waves have had time to reach. If the universe were only 1,000 years old, the radius of our observable universe would be 1,000 light years. But since it is nearly 13,800,000,000 years old, that is the maximum reach of the light we can receive from any direction. Everything beyond that remains, for now, hidden from our eyes. This limit is not just a theoretical curiosity, it determines the boundary of our knowledge. The speed of light imposes a kind of horizon, an invisible wall that marks how far we can observe the universe. No matter how powerful our telescopes are, or how much technology advances, the cosmos has a natural barrier imposed by physics. If one day a signal were to come from beyond that limit, it would mean that the universe is older or different than we believe. Moreover, this speed affects not only light, but all information that can travel through space. Nothing, not even gravity, can transmit information faster. Thus, the speed of light becomes the basic rule of the cosmic game. Everything we see in the universe is a kind of time capsule, limited by that unbreakable rhythm. When we contemplate the most distant galaxies, we are actually looking at scenes from a young universe, because their light has taken billions of years to reach us. What lies beyond that horizon? For now, it is a mystery reserved only for imagination and future science. How many years does the universe really have? It's a question that has fascinated humanity for centuries. For a long time, the best minds in science debated whether the cosmos was eternal, or if, instead, it had a specific beginning. Today, thanks to decades of astronomical observations and advances in physics, we can state it with astonishing precision. The universe is approximately 13,800,000,000 years old. But how do we arrive at such a colossal estimate? The key to knowing the age of the universe lies in observing the oldest light we can detect, the so-called cosmic microwave background, and measuring the speed at which galaxies are moving away from each other. It's as if we are witnessing the fireworks of a gigantic explosion. The farther we look, the further back in time we go, approaching the initial moment of that great expansion we call the Big Bang. Thus, each distant galaxy is a clue in the gigantic puzzle of time. Astronomers have refined their methods by measuring the brightness and distance of stars, called Cepheids and supernovae, true cosmic clocks that help us calculate the time elapsed since the origin. But why does the age of the universe determine the size of what we can observe? This is where physics comes into play. Light, although incredibly fast, does not travel instantaneously. We can only see objects whose light has had enough time to reach us since the Big Bang. In other words, the observable universe is like a gigantic bubble, whose radius is precisely the distance that light has traveled since the beginning of time. As the years go by, that bubble grows because the light from more distant regions finally reaches us. Of course, this calculation is not without challenges. The earliest estimates of the age of the universe varied greatly because they depended on imprecise measurements and an incomplete understanding of cosmic expansion. Today, thanks to space missions like WMAP and Planck, which have studied the cosmic microwave background in detail, scientists have refined the margins of error and consolidated the consensus on those 13,800,000,000 years. However, small disagreements still persist in the scientific community, keeping research and the search for even more precise answers alive. In short, the age of the universe is not just a number. It is the key that determines the limits of our cosmic horizon and the temporal window through which we observe the very history of the cosmos. Every year we discover, every decimal we refine, brings us a little closer to understanding the true size of our observable universe and the mystery of its origin. What is the cosmic horizon, and why does it limit our view of the universe? To understand it, we must first think of the universe as a vast plain shrouded in fog. We can only see as far as that fog allows. In the case of the cosmos, the fog is time and light. The cosmic horizon is simply the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond that limit, what happens remains hidden, as the light from those distant places has not yet had time to reach us. There are two key concepts when we talk about horizons in cosmology: the particle horizon and the event horizon. The particle horizon marks the farthest boundary from which we could have received any signal since the Big Bang. In other words, anything beyond that threshold is, for now, completely invisible and impossible to detect, as the light from those objects has not had enough time to reach us. If the universe were a movie, the particle horizon would be like the edge of the screen. No matter how much you want to look beyond, there simply is no more image. On the other hand, the event horizon represents an even more intriguing barrier. It is the limit beyond which, even if something were to happen right now, we could never receive information about that event in the future. Due to the accelerated expansion of the universe, there are regions so distant that, even if they emit light at this moment, that light will never be able to reach us, not even if we wait for all eternity. It's as if there are messages sent from those areas that are destined to be lost forever in the vastness of space-time. This double horizon defines the observable universe and raises fascinating questions. How much of the universe do we really know? Could there be civilizations, entire galaxies, or exotic phenomena beyond that limit, completely out of our reach? The existence of these horizons not only limits our ability to observe, but also marks a fundamental boundary for physics and cosmology. It reminds us that the universe, while immense, has an edge for our senses and our scientific tools, and beyond that edge, only the realm of speculation and scientific imagination remains. What does it really mean that the universe is expanding? It may sound like the galaxies are simply moving away from each other, as if they were points on the surface of an inflating balloon. But the truth is even more fascinating. It's not that the galaxies are moving through space, but that the very space between them is stretching. This phenomenon, confirmed by the observation of redshift in the light from distant galaxies, transforms our understanding of reality. Can space itself change size? The answer is yes, and it is the foundation of modern cosmology. The expansion of the universe was discovered in the first half of the 20th century, when astronomers noticed that, with a few nearby exceptions, all galaxies seem to be moving away from us. The farther away they are, the faster they are receding. This relationship is known as Hubble's law. But why does this happen? The explanation lies in the fact that the universe is not static, but dynamic. Since the Big Bang, space-time has been in constant expansion, causing the distances between galaxies to increase over time. A surprising aspect of this expansion is that there is no center of the universe from which everything is moving away. If you were in any other galaxy, you would see the same phenomenon. All the other galaxies would seem to be moving away from you. It's like being in the middle of a dough with raisins. As the dough rises in the oven, all the raisins move away from each other, with none occupying a privileged position. This analogy helps to visualize how the expansion affects the entire universe equally. Now, does the expansion of the universe have any limits? Surprisingly, no. In fact, due to the accelerated expansion caused by dark energy, there are regions of the universe that are moving away at such a speed that the light they emit will never reach us. This means that, over time, larger and larger parts of the universe will remain forever beyond our observational reach. Thus, the expansion of the universe not only determines its size, but also the limits of what we can know and explore. There is an invisible boundary in the universe that, although we cannot touch or cross, marks the limit of what we are capable of seeing. The cosmic microwave background. Why is this phenomenon so crucial for understanding the cosmos? Imagine that the universe is a gigantic dark room that suddenly lights up with a faint but persistent glow. That glow is the oldest light we can capture, an echo of the very birth of the universe that has traveled for billions of years to reach us. The cosmic microwave background is, in essence, the radiation that remained after the Big Bang, when the universe was only about 380,000 years old. Before that moment, matter and energy were so densely mixed that light could not move freely, as if trying to escape from an extremely thick fog. But something changed. The universe expanded and cooled enough for protons and electrons to join and form atoms. Suddenly, light could travel unobstructed, filling all space with radiation that, although today is cold and weak, is still present in all directions. And how do we know that this ancient light really exists? In 1965, two scientists, Arno Penzias and Robert Wilson, accidentally detected this faint glow while trying to eliminate noise from an antenna. What they found was a uniform signal coming from all corners of the sky, the strongest evidence that the universe had a hot and dense origin. Since then, the cosmic microwave background has become one of the key pieces for understanding the history and structure of the cosmos. But why is it called the cosmic microwave background? The answer lies in its temperature, just under 3 degrees above absolute zero. This means that its light, originally visible, has been stretched by the expansion of the universe to become microwaves. Observing this background is like looking at an old photograph of the universe, taken when it was still a baby. The tiny temperature fluctuations in this radiation reveal the seeds of the galaxies and the large structures we see today. Thus, the cosmic microwave background is not just an observable boundary, but a window into the distant past, allowing us to trace the early chapters of existence itself. What is the universe really? When we look up at the sky, we might think that everything we see, stars, planets, galaxies, represents the entirety of what exists. But the reality is much stranger and more fascinating. Of all that makes up the cosmos, normal matter, the stuff that forms everything from atoms to entire galaxies, represents only a tiny fraction. How much exactly? Just about 1/20th. The rest is made up of mysterious and almost invisible components, dark matter and dark energy. Dark matter is like a cosmic ghost. It neither emits light, nor absorbs it, nor reflects it. So how do we know it exists? Because it acts like invisible glue. Thanks to its gravity, galaxies can stay together and spin much faster than would be possible with visible matter alone. If we took all the matter we can see, galaxies would simply fall apart. It is dark matter that balances the scales. It is estimated that about a quarter of the total content of the universe is made up of this mysterious substance, although we have no exact idea of what it is made of. Could it be exotic particles yet to be discovered? That is one of the big questions of modern physics. But there is something even more puzzling: dark energy. If dark matter holds galaxies together like an invisible web, dark energy does the exact opposite on a cosmic scale. It is responsible for the universe not only expanding, but doing so at an ever-increasing rate. It's as if space itself is imbued with a strange force that pushes galaxies apart. Can you imagine inflating a balloon and suddenly the air starts coming in by itself and faster each time? That is, in a way, what dark energy is causing in the universe. It is estimated that nearly 7/10 of everything that exists corresponds to this unknown component. Why can't we see or touch these forms of matter and energy? What secrets do they hold? Scientists have devised some ingenious experiments to try to detect them directly, from underground observatories to space telescopes searching for the faintest gravitational traces. However, so far, dark matter and dark energy remain beyond our direct reach. They are like the missing pieces of a cosmic puzzle that, although we cannot see them, we know are there, because without them, the universe simply wouldn't function as it does. The existence of dark matter and dark energy not only redefines our understanding of the cosmos, it also challenges the most fundamental laws and theories of physics. Could there be new forces or particles waiting to be discovered? Or perhaps our view of space and time needs to be completely revised? What is clear is that to understand the true face of the universe, we must continue exploring these enigmas, for within them could lie the key to the greatest mysteries of existence. What happens to the galaxies that are outside the observable universe? This is one of the most fascinating questions in modern cosmology. The observable universe is like a cosmic bubble with a radius defined by the distance that light has been able to travel since the Big Bang until today. But beyond that limit, there are regions, and probably countless galaxies, from which we will never receive information, simply because their light has not had enough time to reach us, nor will it ever due to the expansion of the universe. Does this mean that those galaxies, out of our reach, do not exist for us? In a sense, yes. For any observer, the observable universe is a sphere centered on their own position. The galaxies that lie beyond that horizon are like messages sent from a distant island, but trapped in a bottle that will never reach our shores. Although we know through calculations and theories that there is much more beyond, all direct evidence is forever barred from us. The key to this mystery lies in the accelerated expansion of the universe. The farther we look, the faster the galaxies move away from us, until they reach a point where they are moving at a speed greater than that of light relative to our position due to the expansion of space itself. What does this mean? That even if an advanced civilization in one of those galaxies tried to send a signal, it could never reach us. It's as if the observable universe were a lit stage, and everything that lies outside remains in darkness, inaccessible, but not non-existent. So what consequences does this have for our understanding of the cosmos? On one hand, it reminds us how limited our perspective is, as if we were observing an immense landscape through a tiny window. On the other, it raises profound questions. If the universe is, in theory, infinite or much larger than we can see, how many other worlds, stars, and forms of life will remain eternally outside our knowledge? This frontier is not just geographical, but also existential. It marks the ultimate limit of information, knowledge, and the possibility of discovery. And although we may never cross it, the mere fact that we know it exists invites us to imagine how vast and mysterious the universe is in its entirety. How is it possible that, while confined to a small blue planet, we can know the farthest reaches of the universe? The answer lies in the human ability to observe, measure, and deduce from the light and other signals that travel through the cosmos. Astronomers have developed ingenious techniques to unravel the secrets of the vastness, using all kinds of tools, from optical telescopes to radio telescopes and subatomic particle detectors. Each tool offers a different window into the depths of the universe, as if we had different types of flashlights illuminating hidden aspects in the vast darkness. One of the fundamental techniques is observation through visible light, the same light our eyes perceive. However, the universe does not only speak in colors. What do other forms of light that we cannot see tell us? Infrared telescopes, for example, reveal objects shrouded in cosmic dust or so distant that their light has lost energy during the journey. On the other hand, radio telescopes decipher signals coming from clouds of hydrogen and remnants of galaxy formation. Even X-ray and gamma-ray telescopes capture extreme events, such as exploding stars and black holes devouring matter. But how do we measure such colossal distances? One of the key methods is the observation of type Ia supernovae, which act as cosmic beacons of known brightness, allowing us to calculate how far away they are. Additionally, the use of so-called standard candles and the analysis of the redshift of light coming from distant galaxies has allowed us to construct a three-dimensional map of the observable universe. It's as if, on a dark night, we see the flashes of lighthouses in the distance and, by measuring their intensity and color, deduce how far away they are. Cosmic research is not limited to light alone. Can invisible particles tell stories of the universe? Neutrinos, tiny particles that pass through matter almost undetected, carry information from violent processes inaccessible by other means. Likewise, gravitational waves, detected in recent years, allow us to hear the collisions of massive objects in space-time, opening a new era in cosmic observation. Each method is like a different language, and together they form the most complete narrative we have about the boundaries and content of the observable universe. What does it really mean when astronomers talk about redshift? This phenomenon, fundamental to understanding the structure and evolution of the universe, refers to the stretching of light traveling through the cosmos. When we observe distant galaxies, we notice that the light they emit reaches us with a longer wavelength, meaning it is more shifted towards the red end of the visible spectrum. But why does this happen? The explanation lies in the very expansion of the universe. As space expands, the light waves passing through it also stretch, causing the light to become redder the farther it travels. Imagine a fire truck approaching and moving away from you. The sound of its siren changes pitch due to the Doppler effect. Something very similar happens with the light from stars and galaxies. If a galaxy is moving away from us, its light shifts to the red. If it is coming closer, it shifts to the blue. However, in the universe, almost all galaxies show a redshift, clear evidence that the cosmos is expanding on a grand scale. This discovery, made by Edwin Hubble in the early 20th century, revolutionized our understanding of the universe and its history. What is the practical use of redshift? By measuring how much the light from a galaxy has shifted, astronomers can calculate not only its distance, but also how fast it is moving away from us. It's like having a cosmic ruler and a speedometer at the same time. Thanks to this method, we have been able to map the observable universe, identify the most remote galaxies, and reconstruct the evolution of the cosmos from its earliest moments to the present day. Additionally, redshift allows us to observe the past. As the greater this shift, the older the light we receive. But redshift doesn't just tell us about distant galaxies, it also raises fascinating questions. For example, is there a limit to what we can observe? Are there regions of the universe so distant that their light will never reach us? The answer is yes. Extreme redshift marks the horizon of the observable, establishing a natural boundary beyond which the universe remains hidden, at least for now. Thus, redshift becomes an essential tool, but also a reminder of the limits of our knowledge. How big is the universe really? This is one of the most fascinating questions in cosmology. When we talk about cosmic distances, we enter a scale so immense that everyday measurements, like kilometers or even light years, quickly fall short. To give us an idea, a light year is the distance that light travels in a year, almost 10 trillion kilometers. Yet we still need even larger units to express the true dimensions of the observable universe. This is where concepts like the parsec come in, which is just over 3 light years. Astronomers use these giant units to keep their calculations manageable and understandable. But even so, the numbers can be overwhelming. How can scientists measure such colossal distances? To do this, they employ a kind of cosmic ladder made up of different methods, each suitable for a specific part of the universe. In our galactic neighborhood, for example, parallax is used, a technique that takes advantage of the apparent positional change of stars as the Earth moves around the Sun. For greater distances, they turn to so-called Cepheids, variable stars, whose luminosity allows for remarkably precise distance calculations. And when we want to go even further, we observe Type Ia supernovae and the redshift of light from distant galaxies, which reveal not only their remoteness, but also the expansion of the universe itself. Sometimes the figures can be so enormous that it helps to think in analogies. If the Sun were the size of a marble, the nearest star would be over 300 kilometers away, and the Andromeda galaxy, our closest neighbor, would be over 700,000 kilometers away. These comparisons help us visualize the unimaginable scale at which the cosmos operates. The Milky Way, for example, has a diameter of about 100,000 light-years, and the observable universe extends to approximately 46 billion light-years in all directions. What is the purpose of knowing such enormous distances? Understanding the cosmic scale is not just an exercise in wonder, but it is also fundamental to reconstructing the history of the universe, calculating its age, its size, and even predicting its future. Only by measuring the distance between the most remote objects can we know how the cosmos has evolved and what awaits us beyond. Ultimately, the scale of cosmic distances is the key to deciphering the map of the universe and our place within it. What is the oldest object we can observe in the universe? To answer this question, we must travel back in time, almost to the very moment the cosmos began. After the Big Bang, the universe went through a period known as the Dark Age, a time when there were neither stars nor galaxies, just a haze of hydrogen and helium atoms. But how did the first spark of light emerge in a universe shrouded in darkness? The answer lies in the formation of the first stars, known as population 3 stars. These first stars were very different from those we see today. They contained no metals, as the heavier elements than helium did not yet exist. They were giants, with masses tens or even hundreds of times greater than the Sun, and their lives were extremely brief, lasting only a few million years. Their birth marked the end of the Dark Age and the beginning of the so-called Epoch of Reionization, a crucial period in cosmic history, as their intense radiation transformed the neutral hydrogen in space, allowing light to travel freely and making the universe visible. And what about the first galaxies? The first galaxies emerged when the first stars began to cluster under the influence of gravity. These primitive clusters were much smaller and more chaotic than modern galaxies, but they were the building blocks of everything we observe today in the sky. How do we know all this if they are so far away and so far back in time? Astronomers use telescopes like Hubble and James Webb to capture the oldest light that has traveled for billions of years to reach us. Observing these first galaxies is like looking at an old photograph of the baby universe, capturing fundamental moments of its growth. A fascinating fact is that the light from the first stars and galaxies has been stretched by the expansion of the universe to the point that it now reaches us primarily as infrared radiation. This means that, in a sense, we are observing the past with instruments designed to see what our eyes cannot. The oldest galaxies we have detected formed when the universe was just a few 100 million years old, that is, less than 5% of its current age. Every time we discover a new, even more distant galaxy, we are pushing the limits of the observable and getting a little closer to the very origin of cosmic structures. But what mysteries do these first stars and galaxies still hold? We have yet to directly observe a population 3 star, and its signature remains an enigma that astrophysicists are trying to decipher. However, each technological advance brings us closer to answering questions that once seemed impossible. What was the first light of the universe really like? What processes allowed for the formation of the galaxies that today harbor trillions of stars? The search for the first stars and galaxies is ultimately the search for our own cosmic roots, and each discovery reminds us that, deep down, we are all made of the remnants of those ancient stellar explosions. What happened in the first moments after the birth of the universe? One of the most mysterious and revolutionary stages in cosmic history is the so-called cosmic inflation. Why do scientists consider this brief episode key to understanding the current structure of the universe? Cosmic inflation is a theory that suggests that, a fraction of a second after the Big Bang, the universe underwent an enormous expansion, growing much faster than the speed of light. Although it may seem incredible, this process does not violate any physical laws, as it is not matter that travels faster than light, but rather space itself that is expanding. Cosmic inflation answers several fundamental questions. For example, why is the universe so uniform in all directions? If we observe the cosmic microwave background, the oldest radiation we can detect, we find that its temperature is practically the same at all points in the sky. Without inflation, it would be impossible to explain how such distant regions, which have never been in contact with each other, share the same properties. It's as if two people at opposite ends of a stadium had chosen exactly the same color shirt without ever communicating. And what imprint did inflation leave on the universe we observe today? During that brief period, the tiny quantum fluctuations present in the early universe were amplified and stretched to gigantic scales. These small variations in the density of matter and energy were the seeds of the galaxies, clusters, and voids that today form the cosmic web. Without inflation, the large-scale structure of the universe would be completely different, and there might not even be galaxies as we know them. But how can we be sure that inflation really occurred? Although inflation is a powerful and elegant hypothesis, we are still searching for direct evidence. Scientists hope to find concrete signals in the cosmic microwave background, such as specific patterns of polarization, that could only have been generated by gravitational waves produced during that moment of extreme expansion. Deciphering these signals would be like finding the signature of inflation on the canvas of the universe, confirming one of the most fascinating chapters of our cosmic history. Thus, cosmic inflation not only explains the origin of the homogeneity and structure of the cosmos, but also invites us to continue exploring the secrets that the primitive universe still holds. What are the true limits of our observation of the universe? While the idea of observing to the very edge of the cosmos may seem straightforward, we are actually facing a series of both technological and physical barriers that condition what we can see. For example, even with the most advanced telescopes, we can only capture light and other signals that have had enough time to reach us since the Big Bang. Everything beyond that limit remains, for now, completely out of our reach. The first major obstacle is the very nature of light. Light travels at a finite speed, and the universe has a determined age. This means we can only observe objects whose light, or radiation, has had enough time to traverse the vast distance to Earth. But what if we try to look even further? We would encounter a kind of cosmic wall. The universe was opaque in its first hundreds of thousands of years, so it is simply not possible to see beyond that luminous barrier, known as the cosmic microwave background. What happened before that time is literally hidden from us. But the challenges don't end there. The expansion of the universe stretches light along its path, redshifting it and weakening it to the point that, eventually, it becomes undetectable by our instruments. It's like trying to hear a whisper in the midst of a storm. No matter how sensitive our telescopes are, there is an absolute limit marked by the very physics and current technology. Could we ever overcome these barriers? Science progresses, but we will always have a horizon beyond which we simply cannot look. Adding to this is the background noise. Space is filled with signals, both natural and artificial, that can interfere with our observations. From energetic particles passing through detectors to radiation from our own galaxy, every piece of data we obtain must be carefully filtered and analyzed. Even if we design more powerful telescopes, precision is limited by what we can distinguish between noise and the true signal from the cosmos. Thus, the limits of observation are not just physical boundaries, but also intellectual and technological challenges, reminding us that for now, the universe will always keep some of its secrets. How is the universe organized on the largest possible scale? If you have ever seen an image of the cosmos as a whole, you will notice that galaxies are not distributed uniformly or randomly. In reality, the observable universe resembles a gigantic cosmic web. Why do galaxies cluster into filaments, walls, and enormous voids? The answer lies in the history of gravity and matter since the very origins of the cosmos. Imagine a three-dimensional map where each point represents a galaxy. By connecting the closest points, colossal structures called filaments begin to emerge. These filaments can stretch for hundreds of millions of light years, and between them, enormous regions that are practically empty form, known as cosmic voids. What causes this impressive architecture? During the first moments after the Big Bang, small fluctuations in the density of matter were amplified by gravity. The denser areas attracted more matter, growing and forming the seeds of the galaxies and clusters we observe today. This web, known as the cosmic network, is the most remarkable large-scale structure of the observable universe. The filaments connect superclusters of galaxies, the nodes of the network, while the voids may contain very few or no galaxies at all. It is fascinating to think that visible matter, which forms stars, planets, and ourselves, only represents a fraction of this entire web. Dark matter, invisible but dominant, acts as the skeleton upon which the great structures are built. Is it possible to measure the size of these structures? There are superclusters like Laniakea, our galactic home, which contains the Milky Way and tens of thousands of other galaxies, spanning distances of over 500 million light-years. However, even superclusters are not the final limits. The cosmic network seems to extend as far as our instruments can reach, and possibly beyond. This organization, far from being chaotic, reveals that the universe has patterns and rules, a kind of order in the apparent chaos, guided by the interaction between gravity, visible matter, and dark matter. In summary, large-scale structures show us that the universe is not just an ocean of scattered galaxies, but an immense web where matter clusters following cosmic patterns. Exploring these structures is like deciphering the secret code of the cosmos, allowing us to understand how the universe formed and how it evolves over time. When we think about the structure of the universe, we often imagine galaxies floating in empty space, separated by vast distances. But what happens when we zoom out to the maximum scale? We discover that galaxies are not distributed randomly. Instead, they form gigantic clusters called superclusters. Superclusters are the largest known structures bound by gravity. They contain thousands of galaxies, filaments of gas, and dark matter, stretching across hundreds of millions of light years. Did you know that our home, the Milky Way, is just a tiny part of the Laniakea supercluster? This supercluster is so vast that if we compared it to a city, our galaxy would be merely a tiny house in one of its distant neighborhoods. But what lies between these superclusters? The universe is crisscrossed by immense cosmic voids, regions where almost no matter exists. These voids can have diameters of up to several hundred million light-years, and despite their name are not completely empty. They contain a few scattered atoms and occasionally solitary galaxies that seem lost in the vastness. If we imagine the universe as a three-dimensional sponge, the superclusters would be the dense filaments and knots, while the voids would be the gaps between them. How do we know about the existence of these voids and superclusters? Astronomers have mapped millions of galaxies, and by analyzing them collectively, they have discovered that the observable universe resembles a cosmic web. This web, known as the cosmic tapestry, shows that matter groups into filaments that connect superclusters, while the voids represent the large expanses devoid of galaxies. It is astonishing to think that most of the volume of the universe is made up of these voids, while all visible matter is concentrated in a small fraction of that total space. One of the most fascinating curiosities is that superclusters are not permanently bound. Over billions of years, the accelerated expansion of the universe will cause the connections between them to weaken and eventually disappear from our line of sight. This means that, in the distant future, superclusters will be lonely islands in an increasingly empty ocean. Are we destined to remain isolated in our corner of the cosmos? This is just one of the many questions that arise when exploring the stunning architecture of the universe on a grand scale. How do we manage to peek into the farthest reaches of the universe? The answer lies in telescopes, true time machines that allow us to look back to times when the cosmos was young. Since the invention of the first optical telescope, humanity has refined these tools to capture increasingly faint and distant light. Telescopes not only amplify what our eyes cannot see, they open windows to realities that would otherwise remain hidden. Why are they so essential for understanding the universe? Because the light they collect has traveled for billions of years, and each photon is a messenger from the past. One of the most emblematic examples is the Hubble Space Telescope. Launched in 1990, this observatory revolutionized astronomy by positioning itself outside the Earth's atmosphere, thus eliminating the distortion caused by air. Thanks to Hubble, we have observed galaxies that exist at unimaginable distances, so far away that their light began its journey when the universe was just a fraction of its current age. But Hubble is not alone. The James Webb Space Telescope, with its advanced infrared technology, has made an even greater leap, allowing us to detect objects that are invisible to traditional optical telescopes. What is the secret? The expanding universe stretches light into infrared wavelengths, and only instruments like James Webb can capture it and decipher its secrets. Are there limits to what we can observe? Undoubtedly. Even the most powerful telescopes face barriers, both technical and physical. For example, the opacity of the universe during its first few 100,000 years prevents us from seeing the very moment of the Big Bang. To overcome these limitations, modern astronomy uses telescopes specialized in various wavelengths: radio, microwaves, X-rays, and gamma rays. Each type explores a different aspect of the cosmos and reveals phenomena that would be invisible at other frequencies. Thus, telescopes function as cosmic detectives, gathering scattered clues to reconstruct the universal history. How far can we go with the telescopes of the future? The race to observe the universe beyond current limits is underway. New projects, such as giant ground-based telescopes and upcoming space missions, promise to discover even older galaxies, younger stars, and perhaps answer fundamental questions about our origin. Humanity's ambition to explore the cosmos seems endless, and telescopes are undoubtedly the main bridge between our curiosity and the depths of the universe. What if two distant regions of the universe, so far apart that they could never have communicated with each other, exhibited exactly the same properties? This enigma is at the heart of the so-called horizon problem, one of the most intriguing issues in modern cosmology. At first glance, the universe appears homogeneous and uniform on a large scale. The temperature of the cosmic microwave background, for example, is almost identical in all directions, with tiny variations less than 1/10,000th of a degree. But how is it possible that such distant areas, separated by distances so vast that even light hasn't had time to travel between them since the origin of the cosmos, show such surprising similarity? To understand this dilemma, let's imagine the universe as a huge cake that is expanding rapidly. If two grapes are at opposite ends of the cake, and it grows at a great speed, the grapes can move apart so much that they may never exchange any messages, not even light, since the beginning of the expansion. However, when we observe the real universe, we notice that those grapes share the same characteristics. The horizon problem arises because, according to classical physics, there wouldn't have been enough time, since the Big Bang, for information to travel between such remote regions and achieve this uniformity. Is this just a cosmic coincidence? The answer, according to most cosmologists, is no. The horizon problem suggests that there must be a deeper explanation. This is where cosmic inflation theory comes into play. A phase of ultra-rapid expansion that would have occurred in the early moments of the universe. During this brief period, regions that are now separated by unimaginable distances were, in a distant past, close enough to exchange information and agree on their properties. It's as if, before inflating the cake, all the grapes were stuck together and could share temperature and composition, and only after that moment did they separate at high speed. The horizon problem not only challenges our intuition about space and time, but it also provides a fundamental clue about the processes that shaped the early universe. Solving it helps us understand why the cosmos is so uniform and what physical mechanisms operated in its first seconds of existence. It is a reminder that, although we observe the universe from our limited perspective, the mysteries it hides transcend the limits of the observable and push us to seek new ideas to explain the astonishing coherence of space-time. Have you ever wondered why galaxies move the way they do, or what keeps planets orbiting around the sun? The answer to these cosmic mysteries lies in one of the most revolutionary theories of physics, general relativity. Proposed by Albert Einstein in the early 20th century, general relativity completely transformed our understanding of the universe by asserting that gravity is not an invisible force acting at a distance, but rather the manifestation of the curvature of space-time. Instead of imagining space as a flat, empty sheet, Einstein invites us to see it as a flexible fabric that deforms in the presence of matter and energy. But what does it really mean to curve space-time? Imagine a trampoline. If you place a heavy ball in the center, the fabric sinks, and any small object you put nearby will tend to roll towards the ball. Similarly, stars, planets, and even light itself follow curved paths when passing near massive objects, not because they are attracted by an invisible force, but because they are moving through deformed space. Thus, general relativity explains not only the orbit of planets, but also surprising phenomena like gravitational lensing. where the light from distant galaxies bends when passing near galaxy clusters, allowing us to see distorted and magnified images of very remote regions of the cosmos. And how does this affect the structure and evolution of the universe? General relativity establishes that the universe is not static. In fact, its equations predict that space itself can expand, contract, or even curve back on itself. This idea led to the discovery of the expansion of the universe and laid the groundwork for modern cosmology. Thanks to Einstein's mathematics, scientists have been able to deduce the existence of black holes, regions of space where the curvature is so extreme that nothing, not even light, can escape. Moreover, general relativity is key to understanding galaxy formation, star evolution, and the distribution of dark matter. Without general relativity, our view of the universe would be incomplete and limited. This theory allows us to calculate distances on unimaginable scales, predict the trajectory of gravitational waves, and understand how energy and matter shape the ultimate fate of the cosmos. Can the universe be infinite? Does it have an edge, or does it curve back on itself? All these questions only make sense in light of Einstein's equations, which continue to guide scientific exploration and fuel our wonder at the vastness of the universe. What does it really mean that the universe is expanding at an accelerated rate? For a long time, scientists thought that although the universe was expanding, gravity would eventually slow that expansion down, like a car losing speed while going uphill. However, at the end of the last century, astronomers made an astonishing discovery. Not only is the universe still growing, but it is doing so at an ever-increasing pace. But how do we know this? And what mysterious force is behind this phenomenon? The key lies in the observation of type Ia supernovae, stars that explode predictably and act as cosmic beacons. By measuring their brightness and distance, scientists notice that distant galaxies are moving away faster than what uniform expansion models predict. It's as if someone had pressed the accelerator of the cosmos. This acceleration not only defied expectations, but also introduced one of the greatest enigmas of cosmology: dark energy. Dark energy is a concept that, to this day, remains a mystery. It represents about 70% of the total content of the universe, but it does not emit light, does not interact with matter in a conventional way, and only manifests through its repulsive effect, expanding space itself. If we imagine the universe as a mass of fermenting dough, dark energy would be the yeast that makes the dough grow faster and faster, separating the raisins, galaxies, from each other at an increasing rate. What implications does accelerated expansion have? One of the most surprising consequences is that, over billions of years, many galaxies will move away so far and so fast that the light they emit will never reach us. The observable universe will become smaller in practical terms, isolating future civilizations in increasingly lonely cosmic bubbles. Despite how vast the universe seems today, cosmic acceleration reminds us that we live in a privileged stage of cosmic history, where we can still contemplate much of its immensity. Ultimately, accelerated expansion has forced scientists to rethink many fundamental ideas about the cosmos. Is dark energy an inherent property of space, or is there some unknown field or particle? Could it change in the future, leading to even stranger scenarios, such as the final tearing of the universe? The truth is that while accelerated expansion raises many questions, it also makes the universe an even more fascinating and mysterious place, full of challenges to discover and understand. How far can we look into time and space? Ultra-primitive galaxies are the living relics of the early universe, true cosmic fossils that show us what the cosmos was like after the Big Bang. But how is it possible to detect such remote and ancient objects? The key lies in light. As it travels for billions of years, that light stretches and reddens, allowing us to see the most distant galaxies as they were when the universe was only a few 100 million years old. What do we mean by ultra-primitive? They are galaxies so far away that their light began its journey to us when most stars and planets had not even formed yet. Some of these galaxies, formed just 200 or 300 million years after the Big Bang. Detecting them is as difficult as trying to distinguish the light of a firefly in the middle of a lit stadium. However, advances in infrared telescopes, like the James Webb, have enabled astronomers to identify these jewels of the early universe. What makes these galaxies special? They tend to be small, irregular, and are composed almost exclusively of hydrogen and helium, the simplest elements. They contain hardly any metals or heavy elements because not enough generations of stars had been born yet to create them. In a sense, they represent cosmic laboratories that allow us to study the early stages of galactic formation, the processes of starbirth, and the influence of dark matter on the evolution of the universe's largest structures. Why are we so fascinated by these galaxies? Because observing them is like opening a window to the deepest past. They help us answer fundamental questions. How did we go from a dark and homogeneous universe to one filled with stars, planets, and life? When and how did the first lights of the cosmos ignite? Each new ultra-primitive galaxy discovered is a key piece in the puzzle of our cosmic history. The challenge is enormous, but each advance brings us a little closer to understanding the origin and evolution of the universe we inhabit. What lies beyond the edge of the observable universe? This is one of the great questions that sparks curiosity in both scientists and anyone fascinated by the cosmos. We know that the observable universe is, in fact, a bubble defined by the distance that light has been able to travel from the Big Bang to us. But does something exist beyond this limit? And if so, how could we even imagine it if we can never receive information from those distant regions? The first hypothesis tells us that beyond our observable horizon, the universe simply continues. It's like being in the middle of a vast ocean and not being able to see beyond the horizon, even though the sea keeps extending far beyond where our sight reaches. If the universe is truly infinite, then what lies beyond the limit is more universe, with galaxies, stars, and planets as real as the ones we know, but eternally inaccessible to us. However, we will never be able to confirm their existence, making these regions a permanent mystery. Another intriguing possibility is that the total universe has a shape or structure that closes upon itself, like the surface of a sphere. In this case, if one could travel in a straight line long enough, they would end up returning to the starting point, although this journey is, for now, pure speculation. If the universe were finite but without edges, then beyond the observable limit, there would be no void or wall, but simply more universe that, due to physical laws and accelerated expansion, we will never be able to reach. There are even bolder theories. For example, the multiverse hypothesis suggests that our observable universe would be just a bubble within a much larger ocean, where other universes could exist, each with its own physical laws, constants, and dimensions. Could there be parallel realities so different that we wouldn't even recognize them as universes? Although these ideas sound like science fiction, they arise from mathematical extrapolations and serious cosmological models. However, so far, there is no way to verify their existence or to communicate with those hypothetical neighboring universes. Finally, an inevitable question arises. Why does this limit matter? The answer is that it defines not only what we can observe, but also what we can know. Beyond the cosmic horizon, anything, from galaxies to new laws of physics, remains irretrievably out of our reach. The observable universe acts as a natural boundary for human curiosity, reminding us that, although our vision is vast, there will always be regions of the cosmos that remain forever in the shadows, fueling the mystery and wonder of the unknown. When we hear about the universe, we often imagine an immeasurable vastness. But where are we within that vast stage? The local universe is the cosmic neighborhood we inhabit, a region that, although tiny compared to the entire observable universe, contains astonishing structures and is crucial for understanding our place in the cosmos. What are the boundaries of our immediate environment? What exactly do we mean by local universe? The answer begins with the Milky Way, the galaxy that houses our solar system and billions of other stars. But the Milky Way is not alone. It is part of a group called the Local Group, a collection of more than 50 galaxies bound together by gravity, which includes the Large Magellanic Cloud, the Small Magellanic Cloud, and the Andromeda Galaxy, our enormous neighbor and future companion in cosmic fusion. The Local Group extends over approximately 10 million light-years. Why is it relevant to know the composition and boundaries of this group? Because these gravitational interactions determine the fate of galaxies, influence star formation, and can trigger spectacular events like galactic mergers. And what lies beyond the Local Group? There we find the Virgo supercluster, a gigantic collection of galaxies of which the Local Group is just a small part. This supercluster, in turn, belongs to an even larger structure, Laniakea, the immense heaven in Hawaiian, a colossal network of interconnected galaxies that stretches over 500 million light-years. It is fascinating to think that, despite the unimaginable distance between these systems, they all together form a kind of cosmic web, where each galaxy is like a drop of dew in a vast network of invisible threads of gravity. Our position in the local universe is not random. The forces that keep us here, the distribution of visible and invisible matter, such as the mysterious dark matter, and the constant interaction between galaxies, shape the environment where life has been able to arise. Does our cosmic neighborhood influence the existence of habitable planets like Earth? The answer is yes. The relative calm of the region of the galactic disk where we are has allowed our solar system to evolve without too many cataclysmic disturbances. Thus, understanding the local universe is more than an astronomical curiosity. It is discovering the history of our own cosmic home and its role in the grand tapestry of the universe. The universe, in all its vastness, seems to defy any attempt to find simple patterns. However, there is a fundamental idea in cosmology that has revolutionized our understanding of the cosmos, the cosmological principle. What does this principle really mean? In simple terms, it holds that, on a large scale, the universe is homogeneous and isotropic. That is, if one could move far enough away, it wouldn't matter which direction one looked or from which point one observed. The universe would essentially look the same everywhere. This statement may seem obvious, but in reality, it is one of the boldest and most tested assumptions of modern science. Why is this principle so important? The answer lies at the foundation of all current theories about the evolution and structure of the universe. Without the cosmological principle, modern cosmology simply wouldn't make sense. Imagine a perfectly mixed soup. No matter where you take a spoonful, it will always have the same composition. The cosmological principle tells us that matter, energy, and physical laws are distributed uniformly when we observe the universe on sufficiently large scales, setting aside local differences like galaxies, clusters, and voids. This uniformity allows scientists to extrapolate observations made from our small cosmic corner to the rest of the universe. But how do we know that this homogeneity and isotropy is not just an illusion? Astronomers have gathered evidence by observing the cosmic microwave background radiation and the distribution of galaxies billions of light-years away. Maps of the cosmic microwave background reveal small variations, but overall they show a surprising uniformity. Large structures like galactic filaments and voids may seem enormous, but on a broader scale, they dilute and reinforce the idea that there is no privileged place or special direction in the universe. However, the cosmological principle is not just a mathematical convenience, it also raises fascinating questions. Are there hidden exceptions beyond the observable horizon that challenge this apparent uniformity? Could there be regions of the universe, unreachable for us, where the physical laws are different? Although for now, all observations support the cosmological principle, it remains a hypothesis that science constantly tests. This endless quest to confirm homogeneity, and isotropy not only helps us understand the universe, but also drives the development of new theories and technologies to explore the unknown. The cosmological principle, in essence, is the compass that guides our exploration of the cosmos, reminding us that, on the largest scale imaginable, all points in the universe share the same cosmic stage. What is the oldest light we can see in the universe? To answer this question, we need to go back almost to the beginning of everything, to a time when stars or galaxies didn't even exist. About 13,800,000,000 years ago, the universe was incredibly dense and hot, a kind of primordial soup of particles. However, after about 380,000 years from the Big Bang, a crucial event occurred. The universe cooled enough for protons and electrons to combine and form hydrogen atoms. It was then that light, which had previously been constantly colliding with charged particles, could finally travel freely through space. That primordial light is what we now know as the cosmic microwave background radiation. Why is this radiation so important? Because it is, literally, the fossil echo of the birth of the visible universe. If the cosmos were a dark room and suddenly a light were turned on, the background radiation would be like the flash that still lingers long after the bulb has turned off. This light, although it reaches us today in the form of almost undetectable microwaves, retains invaluable information about the primitive state of the universe, its temperatures, density, and the tiny fluctuations that over time would give rise to galaxies and the entire cosmic structure. How was this microwave background discovered? The answer is as fascinating as it is accidental. In 1965, physicists Arno Penzias and Robert Wilson, while working with a communications antenna, detected a persistent noise that they could not eliminate. After ruling out all possible earthly causes, they realized they were receiving a signal coming from all directions in the sky. It was, unknowingly, the thermal echo of the young universe. This finding revolutionized cosmology, confirming the Big Bang theory and opening a new window to explore the distant past. And what does the observation of this ancient light reveal to us in practice? By precisely analyzing the tiny temperature variations present in the background radiation, scientists have been able to map the universe as it was in its infancy. Those small differences point to the seeds of future galaxies, the places where matter would begin to clump together under gravity. In a sense, the cosmic microwave background is like a photograph of the cosmos' childhood, an image that allows us to understand how, from seemingly uniform and chaotic conditions, all the complexity of the current universe emerged. Thus, the oldest light not only marks the limit of what we can observe, but it is also a time capsule that connects us to the very first moments of the universe. Every time astronomers study it, they decipher a little more of the mystery of our origins and the very fabric of the cosmos. What is the universe really made of? Although at first glance it seems that everything that exists, planets, stars, people, trees, is made of the same matter, the reality is much more complex and surprising. Scientists have discovered that the matter that makes up everything we can see and touch is just a small fraction of the cosmos. We call this matter baryonic. But what does it mean to be baryonic, and what lies beyond what we can directly observe? Baryonic matter is made up of particles called baryons, primarily protons and neutrons, which in turn make up atoms. This matter is responsible for the existence of galaxies, gas clouds, planets, and living beings. However, cosmological calculations show that baryonic matter represents only about 1/6 of all the matter in the universe. It's as if, when opening a toy box, we only found a small bag of pieces and the rest was invisible, yet equally real. Most of the matter in the universe is non-baryonic matter, and this is where things become truly mysterious. Non-baryonic matter primarily includes dark matter, a form of matter that does not emit light or detectable energy. We cannot see or touch it, but its presence is essential to explain the behavior of galaxies and galaxy clusters. If only baryonic matter existed, galaxies could not hold together. They would simply disintegrate due to insufficient gravitational pull. Dark matter acts like an invisible glue that gives cohesion to cosmic structures. How do we know that dark matter exists if we cannot observe it directly? The key lies in gravitational effects. For example, the speed at which stars orbit around the center of their galaxies is much greater than would be possible if only visible matter existed. Additionally, phenomena like gravitational lensing, when the light from distant objects bends as it passes near large concentrations of invisible mass, are compelling evidence. Dark matter, although elusive, dominates the mass of the universe, accounting for about 85% of all matter. Is there still something stranger? Yes. Non-baryonic matter could also include exotic particles that we have not yet detected, such as neutrinos, which constantly pass through the Earth without us noticing. But so far, none of these particles fully explain the mystery of dark matter. Thus, the universe is like an iceberg. The visible part, baryonic matter, is just the tip, while the majority remains submerged in darkness, challenging our understanding and motivating new research at the frontier of science. Is the observable universe the same as the universe in its entirety? This is one of the most fascinating and, at the same time, perplexing questions in cosmology. The observable universe is, in short, everything we can see or detect using light and other signals that have had time to reach us since the Big Bang. It's as if we live on an island illuminated by a flashlight in the middle of a dark and unknown ocean. Only what the light reveals belongs to our observable universe. But what lies beyond that boundary? The total universe, on the other hand, could be much larger, perhaps even infinite. We have no direct evidence of its actual extent, because information from regions beyond our cosmic horizon simply hasn't had time to reach us, nor will it ever if the universe continues to expand rapidly. The fundamental difference lies in the fact that the observable universe is defined by the physical barriers of the speed of light and the age of the cosmos, while the total universe encompasses everything that exists, whether it has been observed or not. This distinction is crucial for understanding our position in the cosmos. For example, we might ask, are there other galaxies, stars, or even civilizations outside our observable universe? The answer, from a physics standpoint, is probably yes, but we will never be able to communicate or exchange information with them. It's as if we are inside a bubble that is growing, but always has a horizon beyond which everything remains unreachable for us. On a conceptual level, studying the observable universe is like reading only the first chapter of a book whose total length we do not know. We know a lot about what is within our reach, but the pages that remain outside will continue to be an absolute mystery. This limitation is not only a scientific challenge, but also an invitation to humility. Everything we believe we know about the universe is just a small fraction of a much vaster and more astonishing reality. What shape is the universe? This question, which seems to come straight out of a conversation among philosophers, is actually one of the great enigmas of modern cosmology. When we talk about the shape of the universe, we refer to its large-scale geometry. Is it flat like an infinite sheet, closed like the surface of a sphere, or open like an endless saddle? The answer affects not only the structure of the cosmos, but also its ultimate fate. The key to understanding the geometry of the universe is the amount of matter and energy it contains. If the universe has enough mass and energy, its gravity could curve space enough to close in on itself, forming a kind of four-dimensional sphere. In this scenario, if you could travel in a straight line for long enough, you would eventually return to your starting point, just like an airplane flying around the world. Conversely, if the density of the universe is low, space would be open and would expand forever, similar to a saddle or an infinite sheet that never curves back on itself. But how do we know which of these shapes describes our universe? Scientists have used cosmic background radiation and the distribution of galaxies to measure tiny variations in the temperature and density of space. The latest results suggest a surprisingly flat universe, with only a minimal deviation, if it exists at all. This implies that the rules of Euclidean geometry, those we learn in school, apply on cosmic scales. Parallel lines never meet, and the sum of the angles of a triangle is always equal to 180 degrees. However, even though the observable universe appears flat, that doesn't mean it is flat in its entirety. The observed flatness could be due to the fact that we are only seeing a small part of the whole, just as the surface of the Earth appears flat in a field, even though we know it is round. Moreover, cosmic inflation, that period of accelerated expansion in the early moments of the universe, would have stretched any original curvature to make it practically undetectable. Thus, the true shape of the universe may lie beyond our reach, hiding secrets in regions we may never be able to observe. The shape of the universe is not just a matter of curiosity. It defines the rules of the cosmic game and the possible futures that await us. If the universe is flat and dark energy continues to dominate, its expansion will never end. If it is closed, it could someday collapse in a big crunch. And if it is open, it will expand forever, but in an even more accelerated and lonely manner. Ultimately, the geometry of the universe is the stage on which the entire cosmic story unfolds, from the first stars to our own place in the cosmos. How fast is the universe expanding? This question, which seems to come straight from one of the greatest cosmic mysteries, has a key answer: the Hubble constant. But what does this often mentioned term in modern astronomy really mean? The Hubble constant is, in essence, the value that indicates the speed at which galaxies are moving away from each other based on their distance. It's as if the universe were a loaf of bread baking, and the raisins inside it were galaxies. The farther apart they are, the faster they seem to separate due to the expansion of the bread itself. This simple analogy illustrates how, by observing the light from distant galaxies, astronomers can estimate the rate of expansion of the universe. But how is the Hubble constant measured? Scientists observe the redshift of the light emitted by distant galaxies. This phenomenon, similar to the change in pitch of a siren as a vehicle moves away, reveals that the light stretches as the galaxies move away. By measuring this stretching and comparing it to the distance of those galaxies, we can calculate the Hubble constant. However, a fascinating dilemma arises here. Different measurement methods have yielded slightly different values. Why does this happen? Is it possible that we are missing a crucial piece in our understanding of the cosmos, or are we simply facing the limits of our current techniques? The value of the Hubble constant is not just a technical detail. It has profound implications for understanding the age, size, and future of the universe. If the constant were higher, the universe would be younger and everything would be expanding faster. If it were lower, the cosmos would be older and the expansion slower. Even a small variation in this number can drastically change our estimates of when the Big Bang occurred or what fate awaits the universe. That's why astronomers devote so much effort to refining their calculations, using everything from observations of the cosmic microwave background to the study of supernovae and nearby galaxies. So why is the Hubble constant so hotly debated today? The so-called Hubble tension is one of the hottest topics in current cosmology. Local measurements, which use nearby stars and galaxies, do not exactly match cosmological measurements based on the microwave background. Are we facing a signal of new, unknown physics, or do we simply need to improve our measurements? Solving this enigma could not only redefine our model of the universe, but also open the door to new theories about its origin and fate. The Hubble constant, far from being just a simple number, is one of the master keys to understanding the universe as a whole. Cosmic darkness is one of the most enigmatic and least understood periods in the history of the universe. What does this mysterious chapter mean? We refer to the era known as the Dark Age, an interval that began shortly after the Big Bang and lasted for hundreds of millions of years. At that time, there were no stars, no galaxies, no planets. There was only a vast darkness dominated by hydrogen and helium, the simplest elements, floating in a practically empty space. If we could travel back in time to that moment, we would see absolutely nothing, not a single flash of light. Why was the universe so dark for so long? The answer lies in the fundamental physics of light and matter. In the beginning, the cosmos was so hot and dense that atoms could not yet form. Protons and electrons, free and energetic, scattered light in all directions, making it impossible for photons to travel great distances. Only when the universe cooled enough did those protons and electrons come together to form the first hydrogen atoms. Light could finally move freely, but there were still no sources to generate it. The universe was like a dark theater before the show began. At what moment did the first light ignite amidst that darkness? After approximately 400 million years, gravity managed to concentrate the primordial gas into increasingly dense clouds. From those clumps emerged the first stars, enormous and ephemeral, which radically transformed the universe. Their ultraviolet light began to dissociate the neutral hydrogen from the surrounding space, in a process known as reionization. It marked the end of the Dark Age and the beginning of a new era of cosmic transparency, when light could travel freely through space, illuminating the first galaxies and shaping the structure we know today. Is it possible to detect signals from that primordial darkness? Although we cannot directly observe the Dark Age, scientists are searching for traces of that period through the cosmic background radiation and the subtle imprints left by the first stars in intergalactic hydrogen. New radio telescopes and experiments aim to capture the faint emission of neutral hydrogen, like cosmic archaeologists exploring the remnants of a hidden past. Thus, cosmic darkness is not only a reminder of our origin from nothingness, but also a scientific frontier, a challenge to human curiosity that drives us to uncover the universe's oldest secrets. What if our universe is not the only one? This is one of the most intriguing questions that modern cosmology dares to pose. The idea of the multiverse suggests that what we know as the universe could be just a bubble within a vast cosmic foam, composed of countless universes, each with its own physical laws, constants, and even dimensions. Why do scientists, traditionally so cautious, dare to consider such an astonishing hypothesis? It all begins with fundamental physics and the understanding of the origins of the cosmos. According to the theory of cosmic inflation, space-time underwent an extraordinarily rapid expansion in the first moments after the Big Bang. Some theoretical models indicate that this inflation may not have occurred uniformly, but rather could have led to separate regions, each expanding like its own independent universe. It's as if space were a mass of dough that, as it rises, forms bubbles, and each bubble is a universe with distinct characteristics. But is there any evidence for the existence of other universes? So far, we have no direct evidence. However, there are phenomena that invite us to speculate. For example, the almost miraculous precision of the physical constants in our universe, which allow for the existence of galaxies, stars, planets, and life, leads some scientists to wonder if there are other universes with different values, where perhaps life as we know it would not be possible. This reasoning is known as the anthropic principle, and the multiverse would be a possible explanation. We live in a universe compatible with life because there are many others that are not. Could we ever communicate or travel to another universe? The answer, for now, is no. Current physics states that each universe would be completely disconnected from the others, separated by insurmountable barriers. Still, some seek indirect traces, such as anomalies in the cosmic microwave background that could be caused by collisions between universes. Although fascinating, these ideas remain in the realm of scientific speculation, closer to the border between physics and philosophy. The multiverse, then, confronts us with an almost existential question. Are we part of a unique reality, or merely a chapter in an infinite library of realities? For now, we can only explore the confines of our own observable universe. But the mere possibility that other universes exist, perhaps radically different from our own, expands our wonder and reminds us that, in cosmology, questions can be even more surprising than answers. What concrete clues do we have that there is a limit to what we can observe in the universe? Even though the cosmos seems to extend infinitely, astronomers have identified signals that reveal the existence of a boundary, the cosmic edge. One of the most notable hints is the abrupt disappearance of galaxies and structures beyond a certain distance. It's as if we were observing a city from a hill, and suddenly, beyond a certain point, fog covered everything. That fog in the universe is the light that has not yet had enough time to reach us from more distant regions. But why does this limit exist? The answer lies in the very nature of light and time. Everything we can see is restricted by the speed of light, the maximum allowed in the universe. If a galaxy is so far away that the light it emitted has not yet had time to reach us since the Big Bang, we simply won't be able to see it. Thus, the cosmic edge is not a physical barrier, but a temporal and spatial horizon. What lies beyond remains, for now, hidden. Another unmistakable signal is the cosmic microwave background. This echo of the primitive universe is, to this day, the oldest light we can detect. Beyond this radiation, the universe was opaque, like a closed curtain before a performance begins. What we receive as microwave radiation is, in fact, the fossil imprint of a time when matter and energy were so densely mixed that light could not travel freely. It's like trying to see through a wall of fog so dense that vision becomes impossible. Could there be indirect signals of what happens beyond our reach? Scientists have searched for unusual patterns in the distribution of galaxies, anomalies in the temperature of the cosmic microwave background, and even fluctuations in the expansion of space-time. Each of these observations acts as a subtle echo that speaks to us of the limit of the observable. Although no telescope has ever captured images of what lies outside the observable universe, its very silence is a powerful signal. A reminder that no matter how far we advance, there will always be a horizon beyond which the universe remains a mystery. In the fascinating study of the observable universe, cosmological paradoxes present themselves as enigmas that challenge our intuition and force us to rethink what we believe we know about the cosmos. One of the most unsettling is the so-called Olbers paradox. If the universe is infinite and eternal, filled with stars everywhere, why is the night sky dark instead of being completely illuminated? The answer lies in the fact that the universe has a finite age and is expanding, which limits the amount of light that can reach us and allows night to exist as we know it. Another paradox that has intrigued generations of scientists is the horizon problem. If we look in opposite directions in the universe, we see regions that, according to calculations, have never been in causal contact with each other, yet show a surprising uniformity in the temperature of the cosmic microwave background radiation. How is it possible that such separated areas are so similar if they could never exchange information? This mystery led to the formulation of cosmic inflation theory, a phase of extremely rapid expansion that may have mixed the cosmos before the horizons separated. The concept of infinity also brings with it profound paradoxes. Consider the duplication paradox. If the universe is truly infinite, is there somewhere an exact copy of you, thinking exactly the same thing at this very moment? Mathematically, in an infinite and homogeneous space, all possible configurations of matter should repeat, leading us to question the uniqueness of our existence and the very meaning of identity in the cosmic context. Finally, the paradox of information in black holes arises, related to the limits of the observable universe. If the information that falls into a black hole disappears forever, does it then violate one of the fundamental laws of physics, the conservation of information? This dilemma not only challenges modern physics, but also reminds us that the edges of human knowledge, just like those of the observable universe, are filled with unanswered questions. Each paradox is, at its core, an invitation to explore beyond, to seek new theories, and to keep alive the curiosity that drives us to understand the cosmos. What do the sun, supernova, and the very early universe have in common? The answer is one of the most mysterious and abundant particles in the cosmos, neutrinos. These tiny particles, which travel almost at the speed of light, pass through matter as if it didn't exist. In fact, at this very moment, trillions of neutrinos are passing through your body without you even noticing. But how can something so elusive be key to unraveling the deepest secrets of the observable universe? Neutrinos are like invisible messengers, coming from the most extreme places and times. They are generated in nuclear processes, such as those occurring in the hearts of stars, in supernova explosions, and even in the first moments after the Big Bang. Unlike light, which can be absorbed or deflected by interstellar dust and gas, neutrinos travel almost unimpeded. It's as if they are privileged witnesses to events that light cannot reveal. This makes them an indispensable tool for astronomers and cosmologists. One of the greatest enigmas that neutrinos help us solve is related to the early universe. Shortly after the Big Bang, the cosmos was so dense and hot that light could not move freely. However, neutrinos could escape and began their cosmic journey just a second after the universe's origin. Detecting these primordial neutrinos, known as the cosmic neutrino background, would be like having an even older and deeper photograph than the one offered by the cosmic microwave background. Although today we cannot directly observe these relic neutrinos, their existence is predicted by theories, and their effects can be traced in how galaxies and large structures formed. Moreover, neutrinos allow us to study extreme phenomena, such as the collapse of massive stars. When a supernova explodes, most of its energy is released in the form of neutrinos. Analyzing these neutrinos on Earth is like receiving a direct signal from the explosion itself, long before the light reaches us. And not only that, neutrinos carry information about processes happening inside the Sun, allowing us to verify theories about nuclear physics and the functioning of stars. Researching neutrinos is a true challenge. They are so elusive that enormous detectors buried under kilometers of rock or ice are needed to capture just a few. But each captured neutrino is a window into the deep past of the universe, to stellar cataclysms and the most inaccessible corners of the cosmos. Ultimately, neutrinos are the invisible pieces that, little by little, help us complete the puzzle of the observable universe. What does the future hold for us in the exploration of the universe? Cosmology, the science that studies the origin, structure, and fate of the cosmos, finds itself at a fascinating crossroads today. Despite the gigantic advances of recent decades, each answer seems to open new questions. How will we be able to see even further back in time, or detect phenomena that are currently invisible to us? In the coming years, cosmology promises to revolutionize with technologies that we are just beginning to imagine. One of the great dreams is to observe the universe as it was before the first stars existed. Upcoming telescopes, such as the Extremely Large Telescope or the future Louvre Space Telescope, will seek to capture the light from the most primitive galaxies and the faint trace of dark matter in the early cosmos. There are even plans to explore the so-called cosmic neutrino background, a kind of echo even older than the cosmic microwave background. Will we ever be able to perceive that radiation that speaks to us of the initial moments of the universe, when everything was chaos and elementary particles? Artificial intelligence is transforming the way we analyze data from the universe, with trillions of galaxies to catalogue and complex patterns that escape the human eye. Machine learning algorithms will be crucial in discovering new cosmic laws or detecting unexpected signals. What if an artificial intelligence is the first to find evidence of life in another corner of the cosmos, or of completely unknown physical phenomena? The future of cosmology could also lie in the detection of high-frequency gravitational waves, exotic particles like axions, or in mapping dark energy and its influence on the fate of the universe. The possibility of building telescopes on the far side of the moon, away from terrestrial interference, would allow us to observe the cosmos with a clarity impossible from Earth. Will we be able to create a complete map of the observable universe, and even glimpse what lies beyond our horizon? The next era of cosmology promises discoveries that, today, we can only imagine. And each advance will bring us a little closer to understanding our place in the vastness of the cosmos. Is it possible that one day the observable universe will become even smaller for us? The answer, though surprising, is yes. The universe, in its accelerated expansion, is separating distant galaxies faster and faster. This means that, little by little, the light from certain regions of the cosmos will cease to reach us forever. Just as on a cloudy night, the lights of a distant city disappear from view, in the future, many galaxies will be hidden behind an impenetrable veil. They will have crossed a cosmic boundary beyond which their light will never be able to reach us. But why does this happen? The key lies in the accelerated expansion of the universe, driven by mysterious dark energy. As space itself stretches, the distances between cosmic objects increase faster than light can travel them. Imagine trying to swim against a current that grows stronger every second. There will come a point where no matter how fast you swim, you will never reach the shore. This is what happens with photons emitted from certain galaxies. The expansion of space exceeds their speed, and they become irretrievably out of our reach. This leads us to a profound question. Does this mean that the observable universe has an end, not only in space, but also in time? The answer is affirmative. In the distant future, astronomers in the universe will see an increasingly empty sky, where only the closest galaxies, those gravitationally bound to each other, will remain visible. Everything else will fade away, not because it has ceased to exist, but because the information can no longer reach us. The observable universe, then, is not a physical boundary, but a boundary of information. What we can know is limited by the laws of physics and the nature of cosmic expansion. This reality poses a fascinating paradox. The further time advances, the less we will be able to know about the universe. Future civilizations, if they exist, will be isolated on cosmic islands, with no way of knowing that there once existed a cosmos much vaster and more diverse. The end of observability is not a cataclysm, but a silent blackout of information, an inevitable consequence of accelerated expansion. Thus, the edge of the observable universe becomes a shadow that slowly advances, reminding us that our access to the cosmos is always temporary and limited. Are we alone in the universe? This question has accompanied humanity since time immemorial and becomes even more fascinating when we consider the limits of the observable universe. The observable universe is like a gigantic cosmic bubble whose radius is determined by the distance that light has been able to travel from the Big Bang to us. Within that bubble, there are hundreds of billions of galaxies, each with countless stars, and potentially trillions of planets. But what implications does this have for life? We know that life, as we know it, requires very specific conditions: a stable star, a planet at just the right distance, liquid water, complex chemical elements. And yet, the observable universe is so vast that even improbable events could happen millions of times. If we think about probability, we might imagine that there are countless worlds where life has emerged, evolved, and perhaps even developed intelligence. But there is an insurmountable limit: the speed of light. If any civilization exists beyond the edge of the observable universe, neither they nor we could ever know about it. It's as if each cosmic bubble were a cosmic island isolated by the ocean of space-time. And what about communication between civilizations within our observable universe? Here another paradox comes into play. The accelerated expansion of the universe is separating galaxies so quickly that, in the future, many of them will be forever out of our reach, even traveling at the speed of light. Imagine sending a message that will never reach its destination because space itself is stretching faster than light can travel. Thus, the window to discover life beyond Earth is not only limited in space, but also in time. The existence of life in the observable universe also invites us to reflect on our own rarity, or perhaps our possible abundance. Are we the result of an exceptional cosmic coincidence, or a common manifestation of the laws of physics and chemistry? The answer remains a mystery, but what is certain is that the observable universe, with its limits and vastness, offers us the perfect stage to explore the big questions about our origin and our destiny. Life, in this context, is not just a biological matter, but a window to understand the meaning of the cosmos itself. Is it even possible to conceive what it would mean to travel to the very edge of the observable universe? Let's think about it. If one could embark on a cosmic journey, leaving our galaxy behind, surpassing clusters and superclusters, moving through the great voids, what would we really be approaching? Not a wall or an abyss, but an invisible limit, determined not by a physical boundary, but by the speed of light and the age of the cosmos. Each step toward that edge would actually be a journey into the past, witnessing how galaxies become younger and more primitive, as if we were turning the pages of a cosmic history book backward. What would we feel as we approached the edge? The light from the most distant galaxies, gently stretched by the expansion of the universe, would reach our eyes tinged with extreme red, increasingly less energetic, increasingly harder to detect. At some point, we would face the so-called wall of the cosmic microwave background, that fossil glow marking the ultimate limit of the observable. Beyond, only absolute darkness. Not because there is nothing there, but because the light from those places has not yet had enough time to reach us. Could we cross that limit? The answer is fascinating and perhaps a bit unsettling. No matter how fast we travel, we will never be able to see beyond the cosmic horizon. It's like standing in the middle of a dense fog. No matter how much you walk, the fog always extends beyond your reach. The observable universe is, in essence, an expanding bubble, centered on us, but not exclusive. Every point in the cosmos has its own horizon. But what if, on this imaginary journey, we could stop right at that edge and look outward? We would see nothing, not even darkness. We would see a total absence of information, the true meaning of absolute void for us. And yet, we know that the cosmos continues, that there are regions, galaxies, and perhaps entire stories beyond our reach, waiting for time and expansion to allow them to be seen, someday, by other civilizations in other places and times. Thus, the journey to the edge of the observable universe is also a reminder of the fundamental limits of our knowledge and of the infinity of what remains to be discovered. What drives our fascination with the universe? Perhaps it is the human desire to understand the unknown, to seek answers to questions as ancient as humanity itself. The observable universe, with its limits imposed by light and time, acts as a kind of cosmic frontier, a horizon to which science and curiosity have allowed us to see. But have we really reached the end of the road, or have we merely opened the first door to an infinite and unexplored mansion? Throughout our exploration, we have discovered that the universe is not only vast, but also dynamic, constantly expanding and transforming. The oldest light we capture connects us to the very origins of space-time, revealing stories of matter, energy, and cosmic evolution. Yet the more we learn, the more aware we become of the immense number of mysteries that still surround us. How far will we be able to observe in the future? What secrets still lie dormant in the farthest and darkest corners of the cosmos? The quest for answers has not only driven impressive technological advancements, such as space telescopes and interplanetary probes, but has also transformed our view of the place we occupy in the universe. We discover that we are part of an intricate cosmic web, where every atom of our body once belonged to a distant star. But what does it mean for humanity to know that there are entire regions of the universe that we will never be able to see or reach? Does this make us insignificant? or does it make us more special for being aware of our own existence and the limits that surround us? Ultimately, the edge of the observable universe is not just a physical boundary, but also an intellectual and philosophical challenge. It invites us to keep exploring, to ask new questions, and to imagine possibilities that surpass our current understanding. In contemplating the universe, we confront the wonder of the unknown and the humility of recognizing that, for now, we have only seen a small part of the grand cosmic work. Perhaps the true journey is not just towards the edge of the universe, but towards the infinite interior of our curiosity.